Now let's study DC machine. Interpolar conductor have maximum flux linkage and minimum EMF induced. Okay. And non-interpolar conductor have a minimum flux linkage and maximum EMF induced. And these EMF induced are trapezoidal AC, and we know the formula NS equals to 120 F by P. From there we can see say F equals to NP by 120. Okay. We use commutator that will convert AC to DC. This does full wave rectification. Okay. Due to this commutator, current remain in the same direction in the conductor under north pole and the conductor under south pole. Current remain in the same direction due to this commutator only. Okay. And this commutator is also called as a mechanical full wave rectifier. Okay. And due to field flux and armature flux are perpendicular and relative motion between them is zero, unidirectional torque is developed. Okay. And we know due to this unidirectional torque, self start. Due to this unidirectional torque, we say DC motor as a self start. Okay. And we know the torque formula. Torque is proportional to the magnitude of field flux and armature flux, and sinusoidal angle between field flux and armature flux. Okay. And and remember one thing, theta electrical equals to P by 2 theta mechanical. Okay. And now let's understand why this interpolar conductor have maximum flux linkage and a minimum EMF induced. See, interpolar axis, this is a interpolar axis. This is also called Q axis, or we can say it as GNA. Okay, geometrical neutral axis. And MNA also lies along this, but due to load it will get shift. Okay. In case of generator, it will shift in the direction of rotation, and in case of motor it will shift opposite direction of motor, MNA. Okay. But GNA and Q axis and interpolar axis is same. GNA interpolar axis and Q axis is same, but MNA will shift accordingly. Okay. And this one is D axis or direct axis. Okay. So interpolar conductor have maximum flux linkage. See, you can see easily out here. See, it is linked with 2 flux. Okay. This one is also interpolar, linked with 2 flux, and non-interpolar conductor is linked with minimum flux. Okay. See, none of the flux is linked is. Okay. So we say it has minimum flux, it is linked with minimum flux. But why maximum EMF, minimum EMF is induced? Maximum flux is linkage with this interpolar conductor, but minimum EMF is induced. We know the formula, induced EMF equals to BLV sin theta, and theta is angle between B and V. This is flux density direction, and the velocity of conductor. Okay. And the velocity of conductor, this is angle between these two. Okay. Velocity of conductor and flux density direction. Okay. So here we can see flux density direction is this one, and conductor velocity of conductor direction is also this one. So the angle between them will be 0. Okay. And in case of angle between them will be 180. So we know that sine 0 and sine 180 is 0. So overall EMF induced will become 0. Okay. That's why we say minimum EMF is induced. Okay. And in case of this one, see, angle between this flux and the direction of conductor is what? 90 degree out here, and 270 is out here. Okay. So due to this we know that sine 90 is what? Sine 90 is 1. So the EMF induced will be maximum. Okay. That's why we say like this. And when we talk about these EMF induced are trapezoidal AC. Okay. This is trapezoidal, this trapezoidal is made purposely, okay, by designing a machine in such a way that we get trapezoidal AC, okay. See, this is how the EMF is induced, okay. This is how the EMF induced, okay. See, this is trapezoidal, okay. Due to its design, due to the nature of design trapezoidal, okay. This is made trapezoidal because we can get higher average value. Higher average value means higher DC we get, and actually what we have to obtain from this DC machine is what? DC output only in case of generator, okay. That's why we make it purposely trapezoidal, okay. And due to this commutator we do full wave rectification of AC to DC, okay. See, due to this rectification we obtained DC, okay. Full wave rectification is done, okay. And and this we have already understood that under north pole or under south pole, direction of the current will remain same in the conductor, okay. Okay, this we have already understood. Position of brush is along field axis, okay, to prevent it from short circuit. Due to short circuit, windings may get damaged, okay. That's why we and symmetrically we say it as it lies in Q axis, okay. In diagram we show it in Q axis, but actually the position of brush is along field axis, okay. See, field axis, this one is field axis. Here we are placing the brush, okay, along field axis, okay. See why it is kept in field axis now. See, and if it is field axis, we know that interpolar conductor have minimum EMF induced. This is the position when minimum EMF is induced and short circuit of coil will not affect will not damage the coil, okay. See, if we short circuit coil when the minimum EMF is induced, then no current will flow, so windings will not get damaged. See, if we place it in Q axis, we know that non-interpolar conductor will have maximum EMF induced. This is the position when maximum EMF is induced, and due to short circuit by the brush, see, short circuit is done by the brush, the windings may get damaged, okay. Now let's understand the construction of DC machine. Basically DC machine looks like this, okay. This one outer part is stator, and this one is a rotor part, okay. Stator is on the yoke. This outer part is yoke. This one is outer part is yoke, okay. Yoke. It is made up of cast iron or cast steel, okay. It provide mechanical support and also the path for magnetic flux. See, for magnetic flux it is providing path. Generally this yoke part is not laminated, okay. Yoke part is not laminated because this does not work on the AC, okay. The only DC is given, okay. It will work on only DC, okay. For more sophisticated machine, this is also laminated, okay. So this one is yoke, and this one is pole shoe, and this one is pole core, okay. From here field flux is induced. See, field flux is induced from here, okay. And this one is armature core. This one is armature core. These are armature slots, and these are armature conductor, armature of winding or armature conductor. And this one is the brush. It is made up of carbon, and this one is commutator made up of copper, and this is insulator. This is mica insulator, okay. There is insulator between the this commutator made up of mica, okay. And this one is a pole arc, okay. This one is pole arc, okay. Area covered by the pole shoe, it is pole arc. And this one is pole pitch, okay. This one is pole pitch. See, pole pitch is bigger than the pole arc. and the ratio of pole arc upon pole pitch should be 0.7. okay, it should be 0.7. Why it should be 0.7, we know. We will study this. See, construction in construction, what we have to mainly remember is that pole arc upon pole pitch is 0.7. Why it is 0.7? To get enough time for current reversal, okay, and a small reactance EMF is induced. For the small reactance EMF, we do these things, okay. See here, if it is very less, so the time reversal is very less, so E is equal to L di by dt. We know that EMF induced, okay, L di by dt. T is very small, so EMF induced will be very high and it will damage the brush, okay, due to sparking. Due to high EMF, sparking will be more and it will damage the brush, okay. If the distance between this is more, then the time reversal, more time to reverse the flux, okay. So E is equal to L di by dt. At T is high, so EMF induced will be low, so brush will get protected, okay. And so in construction we have windings. These are the types of winding: concentrated, distributed, open and closed, okay. And remember that number of commutator segment is equal to number of coil, and back pitch minus full pitch is equal to plus minus 2. If it is plus 2, then it is progressive, and if it is minus 2, then it is retrogressive, okay. And armature windings are always double layer winding, mostly double layer winding only, okay. Armature winding are double layer winding, and it is mainly of two types. One is lap wave and wave, okay. Lap winding and wave winding, okay. Armature winding are of two type, mainly lap and wave. Now, for wave A is number of parallel path, okay. A is always 2. For wave, number of parallel path is always 2, okay, always. For wave, number of parallel path always 2. And we use if we use lap winding, then what happens? See, less current and more voltage, okay. We get less current and more voltage. EMF is more and less cost. Less brush is used, no equalizer is used, okay. These are the advantages, or we can say properties of wave winding. If we do lap winding, then A is number of parallel path is equal to MP. M is plex and P is pole, okay. A is equal to MP. M is plex. Plex means simplex, duplex, okay, triplex. If mostly we have simplex only, okay. So mostly M is 1 only. So therefore A equals to P, okay. So therefore A, mostly we have A equals to P for lap winding, okay. A equals to P, and A equals to 2 for wave winding. And if we use lap winding, then we get more current but less voltage. Number of brush is equal to number of pole is equal to number of parallel path, okay. Remember these things, okay. Number of pole, okay. Next we have armature reaction. This is the most important topic in theory of a DC machine, okay. Armature reaction is effect of armature flux on field flux, okay, is the armature reaction. And armature flux is always more than the field flux, okay. And effect of armature reaction are magnetization, demagnetization or cross magnetization. Magnetization means what? Magnetization means armature flux will support the field flux, okay. Magnetization, it means magnetization means armature flux is supporting the field flux. Armature flux is opposing the field flux, means demagnetization. And when they are perpendicular to each other, armature flux and field flux are perpendicular to each other, then it is called cross magnetization. And we know in case of DC machine we have no magnetization and and demagnetization. Only we have cross magnetization. We know that field flux and armature flux are perpendicular to each other, so there will be cross magnetization only, and this effect is in DC machine only. Okay, this is seen in DC machine only. Okay. So we have these two are perpendicular, so due to this cross magnetization, see what are the things we have to we see. Okay, we have saturation of core. Okay, and MNA gets shifted with respect to GNA. Okay, let us understand due to shifting of MNA. See how MNA is shifting. In case of generator, MNA will shift in the direction of rotor, in the rotor direction. Okay, and in case of motor, MNA will shift in opposite direction of the rotor, and its intensity of shifting will depend on the load. If there is more load, then shifting of MNA with respect to GNA will be more. Okay. And due to this shifting, demagnetization will occur. Okay, because conductor between MNA and GNA are responsible for demagnetization. Okay, this demagnetization, and also it leads to the commutation problem, because brush were fixed at field axis considering MNA is on the GNA, but MNA has shifted. Okay, that's why commutation problem is also seen. And there are two type of demagnetization. So see, demagnetization due to the conductor between MNA and GNA, and also demagnetization due to saturation of core is also seen. See, saturation of core means weakening of field flux, so therefore demagnetization. Let us understand this one, saturation of core. Here we can see the saturation of core. See, due to this shifting of MNA, consider this is a generator. Okay, and its rotor direction is this one. This one is the rotor direction. Okay, this one is the rotor direction. So MNA is shifted in the direction of rotor. Okay, and see here we have the saturation. Due to this saturation, weakening flux will get, field flux will get weak. Okay, due to this weakening of flux, demagnetization occur. Okay, this is for the saturation of core. Okay, and trailing tip will have the saturated part. Okay, trailing tip will have saturated part. See, trailing tip has a saturated part, and leading tip has a unsaturated part. See, leading tip, trailing tip. Okay, in case of motor, what we will have? In case of motor, if we have the this direction, then MNA shifting will be this one. Okay, so MNA shifting will be this one. If MNA shifting is this, then the core saturation will occur here, core saturation will occur here. Okay, otherwise we can say in case of motor, everything remains same, only the direction of rotor will be this one. Okay, only the direction of the rotor will be this one. MNA will remain here. Okay, for generator, shift of rotor is in the same direction, for motor in opposite direction. Okay, so these are the things. See, another type of demagnetization, conductor between MNA and GNA responsible. See, this is the conductor between MNA and GNA. This is, due to this also demagnetization occur. Now we can understand the two type of demagnetization. One demagnetization was due to saturation. Okay, and this one is due to shifting of MNA and GNA. Okay, due to this conductor demagnetization. See, due to this flux will be like this. Okay, due to this flux will be like this. See, flux is like this, means it will oppose the field flux. Opposing field flux means demagnetizing. Okay, this is what we have to see. So now we have to counterbalance this commutation problem and demagnetization and cross magnetization. Okay, to solve the problem of cross magnetization, demagnetization and commutation, we use interpoles and compensating winding. Okay, interpoles is connected in series with armature. Okay, and it is 1.2 to 1.3 times interpole armature MMF. to handle armature flux and reactance mmf both. Okay. Mm. In that way it will address cross magnetization at interpole and reactance emf. Reactance, if we improve reactance, if we reduce reactance emf, then it will improve commutation. Okay, if we improve cross magnetization at interpole, it will improve commutation, and also it will reduce armature emf. Okay, so overall we have maximum advantage we got from interpole is that we improved commutation. Okay, and in one case we have reduced the armature effect. Okay, so overall we say it as interpole help us to improve commutation. Okay. Now when we talk about compensating winding, it is connected in series with armature winding. Okay, it is also connected in series with armature winding. It will address cross magnetization at cross magnetization a part of interpole. A part of interpole, cross magnetization a part of interpole, and demagnetization of field flux. Due to this we have reduced armature effect. Okay, reduce armature reaction effect, and due to this thing, due to cross magnetization at a part of interpole, we have reduced armature reaction effect, and also it improves commutation. So overall we can say for compensating winding it will reduce armature reaction effect. Okay, so for interpoles plus compensating winding is used in large DC machine. Okay, only interpole is used in small DC machine. Okay. When we talk about how it look like, see, this one is interpolar, this one here we have interpole. Okay, here we have interpolar winding, and this one is compensating winding. See, this one is compensating winding. Okay. Armature reaction effect by waveform. Okay. Main thing what we have to remember here is that shape of armature mmf is triangular, and shape of field flux is trapezoidal, and shape of resultant flux is this one. Okay, due to saturation it become it is also triangular, but here we have saturation. Okay. So when we talk about armature reaction effect, a single coil armature mmf is rectangular, but practically many coils are there. Okay, so due to many coils we have this thing. Okay, so we have, due to many coil we have overall triangular. Okay, overall triangular. Okay, and for field flux is trapezoidal, and armature and when we talk about emf induced, that is also trapezoidal AC. Okay, that is trapezoidal AC. Okay, induced emf. And resultant flux is also a triangular, we can say. So finally remember that armature flux is triangular in nature, and it is peak at MNA and Q axis, and field flux is trapezoidal in nature, and it is zero at Q axis and MNA, and the resultant MMF is flat top triangular. Okay, and is flat top triangular, and induced EMF in the armature coil is trapezoidal AC. Okay, let's study the working of DC machine briefly. Okay, see, this is the structure of DC machine as we have already discussed. We have already discussed the working of basic generator and basic motor. Okay, this is also same, here also we have same. Okay, as we have studied that in case of generator, obviously we will have generating action. okay. um, and we will have also a motoring action in the generator due to Lenz law, okay. And when we talk about motor, obviously we will have motoring action, and due to Lenz law there we will have generating action also, okay. So in the same way, we have in the DC machine also. Let us study let us first discuss about a generator, okay. Let us first study about the generator. Suppose this is a DC generator, okay. And in generator what we do, we provide mechanical output and we take electrical output, okay. We give mechanical input and we take electrical output. See, this is for field, okay. This one is for field pole, okay. In here we will provide DC input. Here we will provide DC input, whether in case of motor or a generator. Here we will provide DC input. Due to DC input, field will field flux will flow from north to south, okay. Field flux will continuously flow. And this one we have armature, this one we have armature. Here in we have turns, coils, and like this we have, okay. So these are stationary, and when we provide mechanical input it will start rotating. Due to this rotation, there will be continuously change of flux in the coil, okay. And we know according to the Faraday law, when a conductor is placed in changing magnetic field, EMF is induced, okay. So the EMF will induce in the coil, and that induced EMF will be AC in nature, okay. And that EMF that coil is connected to this commutator, and commutator is externally connected to brush, okay. And this commutator will convert that AC to DC, okay, that DC, and we will get DC output from these two bus, okay. Brush, okay. So finally we obtained output, DC output, and when we connect this DC output in the load, a current will start to flow in the armature coil, okay. Due to this current in the armature coil, EMF flux will produce, armature flux will produce, and and we have already the field flux, and due to this interaction of field flux and armature flux, a torque is electromagnetic torque is produced that will oppose the prime mover torque of this generator, okay. So in this way we understood. First we generated EMF, and due to that load, and we connected load. Due to that load, current flow, and due to that current, armature flux, and due to interaction between armature flux and field flux, a further torque is produced that will oppose the prime mover. So finally we saw both motoring action and generating action is present in case of generator, okay. So when we talk about motor, in the same diagram we can explain the motor also, okay. In motor what we will give, see, in motor also we will provide DC input to this field winding, okay. And we'll provide DC input to this brush. When we provide DC input to this brush, when we provide DC input to this brush, it will convert. Due to this commutator, this armature winding will receive receive the EMF, okay. Receive EMF, and due to this current will flow in the armature. Due to this current, flux will produce, armature flux will produce. Due to the armature flux, there will be interaction between field flux and armature flux. Due to interaction between field flux and armature flux, a torque is developed. Due to that electromagnetic torque, it will start rotating. Due to this rotation of armature conductor and this stationary field, a further EMF is induced in the coil, and this induced EMF is back EMF, and this induced EMF will oppose the input EMF, okay, input EMF that we provided, okay. that is the cause of that is due to Lenz law. Okay, according to the gate point of view, EMF equation, torque equation, equivalent circuit of all type of DC machine, most importantly characteristic of DC machine, that is motor or a generator, characteristic of motor and the generator. These are the most important part according to gate point of view. Okay, so let's start from EMF equation. When we talk about EMF equation, EA, that is back that is EA is armature EMF. Okay, EA is equal to Ka phi omega m. Okay, Ka phi omega m. Ka is PZ upon 2 pi a, that is P is number of pole, Z is number of conductor, A is number of parallel path, and phi m is flux per pole, and omega m is mechanical angular speed of a rotor. And we know mechanical angular speed, and we know electrical speed of an electrical speed is 2 pi f. Okay, similarly we can say 2 pi, and in place of f we can put np by 120, and np by 120, and we know this whole is in this whole was in electrical, so to convert into mechanical we will multiply it by 2 by p. So finally we get omega s is equal to 2 pi n by 60. This thing we have to remember, very important. Omega equals to omega m equal to 2 pi n by 60. And when we talk about torque equation, we have T equals to Ka phi Ia. Ka phi, see Ka and phi is same as it is what we have studied here. Okay, Ka and phi is same, and Ia is armature current. Okay, and in case of series we have T equals to Ka, and phi is a function of Ia. Okay, phi is a function of Ia, that is phi equals to Kia. Okay, that's why we have Ka Ia square. Okay, this thing you have to remember for series, in case of series. Okay, so when we talk about types of DC machine, we on the basis of excitation. On the basis of excitation means on the basis of field that we are giving. Okay, so we have mainly we have two types. We have separately and self-excited. Okay, we have separately and self-excited. When we talk about self-excited, further classified into shunt, series and compound. So finally we have separately shunt, series and compound. Okay, and compound is further classified into cumulative and differential. These are the main types of DC machine that we need to keep in mind. Separately shunt, series, cumulative, differential. Okay, these four types: separately shunt, series, cumulative, differential. This thing you have to remember. And here let us study about the equivalent circuit and equations. Okay, equivalent circuit and equations of these machines. Okay, when we talk about separately means by the word itself we can make out that field is separately excited. Okay, there is no relation between their armature and all. Okay, it is separately excited. See, field is separately excited out here. Okay, and this one is armature, this one is armature resistance. Okay, so accordingly we can easily say that if we increase the load, suppose this we are studying for a generator. Similarly it's for motor also. Okay, let's consider all our generator. Okay, this is the field with increase in load. If we increase in load, flux will remain constant. See, flux remain constant with increase in load. And similarly we can write the equation EA equals to VT plus IA RA plus voltage brush drop voltage. Okay, this part. Okay, see, this EA and this EA is same. Okay, we can equate this part with this part. Okay, so this concept is used in the questions, so keep in mind. Okay, and when we talk about shunt, it is shunt means field. Shunt field is connected in parallel with the terminal. And for series, field for series motor, field is connected in series with the armature. Okay, and for cumulative and differential, what we have to mainly remember is that for cumulative, flux will get added. For cumulative and differential, basically it has both series and shunt. It has both series and shunt field. Okay, and for cumulative, both series and shunt are added, and for differential, series flux is subtracted from the shunt flux. Okay, this is the main point that we need to keep in mind. Okay. And for when we talk about their diagram, we have this is the diagram. See, when they are added, cumulative means added. Okay. See, if we see any field this way, no, then it will get added. See, here it is subtracted, means here we have and here we have the point. Okay, so it gets subtracted. Okay, so overall flux will get decreased out here in case of differential, and here overall flux will get increased in case of cumulative. Okay, and further we have a long shunt and short shunt. See, when the shunt part will connected far from the armature, see, shunt part, between that there is series also. Okay, so it is connected far, it means long shunt. Okay, when this is connected near to the near to the armature, then we say it as short shunt. Okay, and here also see, when we connect this out here, okay, then it will become short shunt. Okay, so difference between long shunt and short shunt is only this one difference, connection of this shunt part. Okay, and everything working and part and everything will remain same for long shunt and short shunt. Here we have shown the long shunt diagram. Okay, so we can consider short shunt also, nothing will change. Okay, working part, all everything will remain same. Okay, above this we have long shunt, and RSC is near to the armature in case of short shunt. Okay, and if see, field is get adding phi sh plus phi se, and in case of differential, field is getting subtracted phi sh minus phi se. Okay, with increase in load, field will get increase in case of both the type of machine. Okay, everything. So similarly we can also say the equations. Okay, EA equals to VT plus IA into RA plus RAC plus voltage plus drop. Okay, so when we talk about shunt part, see, with increase in load, shunt flux will remain constant. Okay, and equation is same as it is. Okay, and for series we have different. Okay, for series what we have different, with increase in load phi se increases, and its equation is also different. Okay, so finally, according to the equivalent circuit, what we can say, these two separately and shunt are similar. Okay, and series and compound are similar. Okay, and this we can make out. See, with increasing load phi se increases, with increasing load phi se increases. Okay, what here, field remain constant in both case. Okay, when we talk about characteristic of these machines, these four machine, when we talk about characteristic of these four machine, in characteristic what we study is no load characteristic, load characteristic, external characteristic, and armature characteristic. That is also called internal characteristic. This armature characteristic is also called internal characteristic. Okay, this thing we need to keep in mind. And one most important thing that we need to keep in mind is that accept external characteristic of these machines, accept external characteristic of these machines. Okay, these four type of 1 2 3 4 type of machine, all characteristic are same. Okay, all characteristic are same except this external characteristic. Okay, all characteristic means no load and internal, that is armature characteristic. No load and armature characteristic is same for separately, shunt, series, and compound generator. Okay, So let us study one by one. Let us study all the characteristic for separately. Okay, we will say it as same for shunt, series and compound, except this an external characteristic. Okay, let's study all the characteristic for separately excited. See, for no load, this is for no load characteristic. No load characteristic means EA versus IF, armature EMF versus field current, and load characteristic means terminal voltage versus field current, and external characteristic means terminal voltage versus armature current, and armature characteristic means field current versus armature current. Okay. So when we talk about no load characteristic means no load is connected. Okay, when no load is connected, in case when no load is connected and field is zero, then also some EMF is induced, that is due to residual flux. Okay, due to residual flux EMF is induced. See, at zero field current, still EMF is induced. This is due to residual flux, and when we keep on increasing the field current, then the EMF, then the EA will increase, and at a point it will become constant due to saturation. Okay, due to saturation it will become constant. Okay, see, when we connect load, that is IA, due to IA RA drop, it will start from here. Okay, everything will remain same, VT versus IF. Okay, so this is a load characteristic and this one is a no load characteristic. See, everything remains same. Okay, EA is directly proportional to IF, only up to saturation. Okay, only up to saturation point they are proportional. Okay, only up to saturation point. After that EA will remain constant. With whatever we will increase in IF, EA will remain constant. Okay. So when we talk about external characteristic, that is terminal voltage versus IA, as we know that as we increase IA, phi A will increase and armature reaction will also increase. Due to increase in armature reaction, overall phi will decrease. If we decrease phi, then armature reaction drop. Okay, due to armature reaction drop, this is the line. Okay, this is the line due to armature reaction drop, and this one is due to IA RA drop. Okay, with increase in IA, VT will, terminal voltage will increase. We know with increase in load, terminal voltage will decrease. So this is the characteristic for external, and for internal, that is armature characteristic, IF versus IA. At with increase in IA, we know that VT will decrease. Okay, to make VT constant, what we have to do is we have to increase IF also. See, we are increasing IF. With increase in IA, we are increasing IF also. To increase EA, we have to increase IF to increase EA, so that VT will remain constant. See, this is the diagram for armature characteristic. See, this no load and armature characteristic is same for shunt, series and compound. So next what we will study is external characteristic for shunt, series and compound. This only we have to study. So now let's study external characteristic of shunt generator. Okay, but before that we have to remember a point. Okay, voltage build up in DC generator. This is the very important point we need to remember. Okay, voltage build up in DC generator. What are the conditions for voltage build up in DC generator? Okay, this is a very important point. For the condition are residual flux and field flux should support it. Okay, residual flux should be in the same direction as a field flux direction. Okay, for the voltage build up in generator, DC shunt generator, and shunt resistance should be less than the critical shunt resistance. Okay, and mechanical speed should be greater than the critical mechanical speed. Okay, for a voltage see, this is the diagram of external characteristic of DC shunt generator. See, with increasing load we have a decreasing slope. Okay, we have a decreasing slope. Okay, this is a critical load. Okay, above this voltage build-up will not be possible. Below this only voltage build-up will be possible. Okay, and for DC series, see, we know that in case of DC series generator, field winding is corrected in series. Okay, so due to IA only their field will exist. Okay, with zero IA, due to residual flux, EMF is induced. See, it is similar to no load and load characteristics. See, at zero IA, still EA is developed due to residual flux, and with increase in IA, EA will increase till the saturation point. Okay, after that it will remain constant. Okay, see here IA and IF is same. Okay, we know. See, IA and IF will remain same obviously for DC shunt, so for DC series motor. Okay, generator. So next let's study external characteristic of compound. Okay, external characteristic of a compound. Here we have the external characteristic of compound. External characteristic of a compound means terminal voltage versus armature current. Okay, we have over compound, level compound, and under compound, and differential compound. We know that differential compound means what? Phi SH minus Phi IC means very less, means least flux is there. Okay, due to least flux, least EMF is induced. Due to least EMF, least external voltage will be there. Okay, so it is at the bottommost. Okay, bottommost part. See, with that logic we say like this. Okay, and for over compound, the rate of increase of EA is more than the rate of increase of IA into RA plus RAC drop, so VT will increase. For level compound, rate of increase of EA is equal to rate of increase of IA into RA plus RAC drop, so VT will remain constant. And for under compound, rate of increase of EA is less than IA into RA plus RAC drop, so VT will decrease. Okay, so now let's next study about the characteristic of DC motor. Okay, so here also we will study DC motor like separately excited, shunt, series, and compound. Okay, these are the four main type of motor. Okay, separately, shunt, series, and compound. In here also, and in DC motor characteristic, what we have to study is speed versus armature current, torque versus armature current, and speed versus torque. These three characteristics we have to study for all. Okay, and remember one most important part is that for separately excited and shunt, for separately excited motor and shunt excited motor, characteristic remains same as it is. Okay, characteristic remains same as it is. We have different characteristic for DC series motor and for compound, and for DC compound motor. Only this part is same. Only this part is same. Okay, for DC compound motor, torque versus IA is same as a shunt. Okay, and we have different characteristic for torque versus speed versus IA and speed versus torque. Okay, speed versus IA and speed versus torque of a compound DC motor is same. Okay, speed versus IA and speed versus torque of a compound DC motor. Let us see this and complete this out here only. Okay, See, we know that according to the field, when we talk about the field flux, okay, we know that field flux is minimum in case of a differential, because they are subtracted, okay. Because we know in case of differential, what happened is that phi sh minus phi se, that's why we have the minimum flux there, okay. After that, what we have, for shunt, okay. See, we know that if the flux is minimum, field flux is minimum, means more speed, okay. Field flux minimum is more speed. See, field flux minimum is more speed. Okay, and after that we have the highest flux, we have the highest flux in cumulative. See, we have the highest flux in cumulative, so it is at the bottommost part, okay. For uppermost part we have a differential and shunt, and then cumulative compound, okay. This is the logic behind this, okay. And when we talk about with increase in torque, obviously the speed will decrease, okay. This is the most common thing that everybody's know, okay. So let us study for separately excited, okay. Speed versus armature current. We know that see, one strange thing out here is without with increase in IA. See, here we have upper part is for with armature reaction, with considering armature, and without considering armature. As a logically straight, we will think like that. And this will come here, and this will come here, okay, without armature reaction and with armature reaction, okay. But here we have opposite. This we have to keep in mind, okay. Speed versus IA. With increase in load, obviously the speed will decrease. See, this is the logic, very simple logic we have, okay. With increasing load, the speed will decrease. So, okay, at zero load, speed will be rated, that is full speed, okay. And with increasing load, speed is decreasing out here, okay. And when we talk about speed versus torque, with as we increase a torque on a DC motor, okay, obviously its speed will what, decrease. See, speed is decreasing with increase in torque, okay. And when we talk about torque versus IA, with increase in IA, torque will also increase, okay. Torque will also increase without, if we will not consider the armature reaction, then it will be straight, okay. But we have armature reaction also, so it will bend afterwards, okay. After some point it will bend, okay. So with increase in IA, torque will also increase. It is linear without armature reaction, but we have armature reaction, that's why it will bend, okay. And for DC shunt motor, same thing we have to study for DC shunt motor, keep in mind. And for DC series motor, we have same characteristic for speed versus IA and speed versus torque, okay. Keep in mind that we cannot operate DC series motor without load, okay. We cannot operate DC series motor without load at zero load, or at zero IA or zero load. It's because its speed is infinite, and motor may get damaged due to very high speed, okay. That's why we cannot operate at zero load or zero torque, okay. We cannot operate motor. So see, at zero IA and T torque, we have infinite speed, and as we keep on increasing the torque or IA, armature current, speed will start to decrease, okay. Speed will start to decrease at infinite current. At infinite armature current, we have minus IA upon IA plus RAC upon K dash, okay. This is the formula, okay. So for DC series motor, torque versus IA, we have like this, okay. Due to saturation, it will come here, okay. Due to saturation, it will come here, okay. And we know that in case of DC series motor, field winding is connected in series with the armature, okay. That's why we have a torque equation like this, okay. And torque is directly proportional to armature current, square of armature current, okay. In other motor, we have torque is directly proportional to armature current, but in case of DC series motor, torque is directly proportional to square of armature current. See, square of armature current. At zero armature current there will be no torque, there won't be any torque at zero, and as we increase it, torque will also increase. Okay. This is the main point we have to remember. So finally what we have studied is for DC, for separately and shunt, characteristic is same, all characteristic is same for separately and shunt, and torque versus Ia of a separately is same as torque versus Ia of compound, and for compound we have speed versus Ia like this. It is very simple one. Only we have to remember is this one and this one and this one. Okay, this for this is series and this for compound. Okay, so you have to see most of the questions are these all are for of gate. This green one is gate, this one is for ESCC. Most of the questions are asked from this topic. Now let's study about the power loss efficiency in DC machine. Okay, when we talk about power loss in DC machine, we have 5 types of losses. Okay, copper loss that happens in armature winding and field winding, that is for armature winding we have Ia square Ra, and for field winding we have If square Rf. Okay, and copper loss is core loss is hysteresis and eddy current loss. Okay, hysteresis, we know that the eddy current loss is proportional to F square for constant flux Bm. Okay, for constant Bm, eddy current is proportional to F square and hysteresis is proportional to F. Therefore we know that these core loss depend on the frequency. Okay, and frequency happens only in case of AC, and we know that there is no such AC in case of field winding. Okay, so there is no core loss in field core. Okay, field pole. Okay, so core loss occur only in armature and face of the pole. Okay, only in armature and face of the pole core loss occur. And mechanical loss is friction windage loss and brush drop. We know approximately we take it at 2 volt, and stray load loss are mostly neglected. It is considered only when it is given in the question. Okay, so these are the losses, 5 types of losses that we need to keep in mind. And when we talk about power flow diagram of generator, we have first we give mechanical input, so stray load loss is subtracted, and then mechanical loss, after that core loss, and then brush drop loss, and then ohmic loss, and finally we get power output. Okay, and for a motor, if we talk about motor, we just go from opposite side. Okay, opposite side we give this is power out, this is electrical. For motor, this is this power output is mechanical, and this is electrical input. Okay, this is electrical input, and just we will reverse these losses. Okay, this will come here and this will come here. Everything is same except this one. Core loss will come here, voltage brush drop will come here. Okay, and electrical input out here, and power output we will get here. Okay, so only this difference is there in motor, in case of motor. And when we talk about maximum power output in DC machine, talk about maximum power output DC machine, we know that first let us consider for a generator. Okay, we know that for generator power output is what? For generator, P power output is terminal voltage into armature current. Okay, VT Ia, power output of a generator is VT into Ia. Okay, power output of generator is VT into Ia. For maximum condition, for maximum power output is when when Ia is equal to Ea upon 2 Ra and Vt is equal to Ea upon 2. Okay, and we know that power output is Vt into Ia, and when we multiply these two we get Ea square upon 4 Ra. See, Ea square upon 4 Ra for generator. Maximum power output is Ea square upon 4 Ra, and similarly for motor we know that power output means Ea upon Ia. Okay, Ea upon Ia, and condition for maximum power output is Ia should be Vt upon 2 Ra and Ea should be Vt upon 2, and power output, therefore maximum power output will become when we will multiply these two, Vt square upon 4 Ra. See, Vt square upon 4 Ra. And remember one thing, when we will get maximum power output from a DC machine, whether it is motor or a generator, its efficiency will become 50%. Okay, remember these things, its efficiency will become 50%. And if we want to take maximum efficiency from the machine, we have to do variable loss equals to constant loss. Variable loss, we know that copper loss are variable loss. Okay, variable loss is Ia square Ra equals to core loss, that is core loss plus mechanical loss is constant loss. Okay, this should be equal. Okay. So next we will study about the speed control of a DC shunt motor, separately excited motor, and a DC series motor also. Okay, speed control of these type of motor, this shunt series separately excited. Okay, this we will study. See, when we talk about speed control of a DC motor, we have variable voltage method, variable armature resistance method, and we have variable flux control method. Okay, variable flux control method, terminal voltage control, armature resistance control, and flux control. Okay, field flux control. These three are the method of speed control of a DC motor. Okay, and basically variable voltage means we decrease the voltage. Okay, we decrease the voltage. Okay, and for variable resistance we increase the resistance, and for variable flux means we decrease the flux. Okay, and remember one thing, variable voltage means decreasing the voltage, and variable resistance means increasing the voltage. With this we get speed. With this we get speed below the base speed at the constant torque. Okay, and variable flux means decreasing the flux. With this we get speed above the base speed with constant power. Okay, with constant power. This basic thing we have to remember. And how this happens, let us discuss. Okay, when we decrease the voltage, when we decrease the terminal voltage of a motor, an armature current will decrease. Okay, if armature current decreases, then torque will decrease. You only think if torque will decrease, then obviously electromagnetic torque will be less than the load torque, therefore speed will obviously decrease. Okay, and speed decrease is hence this speed decrease is below the base speed at the constant torque. Okay, at the constant torque. This point you have to remember. And if for variable voltage method we decrease the voltage, so we get speed below base speed at the constant torque. This point we have to remember. And when we increase the armature resistance, an armature current will decrease. If armature current decrease, torque decreases, and therefore speed will decrease below the base speed at the constant torque. Okay, and if we decrease the flux, induced EMF will decrease. Okay, if induced EMF decrease, then armature current will increase. If armature current increases, then torque will increase. Okay, and then induced torque will increase. If torque increases, then then speed of the motor will increase, that will be above the base speed with constant power. This point you have to remember, with constant power. Okay. So finally we understood that for variable voltage control, we decrease the voltage, we get speed below base speed at the constant torque. For variable resistance method, we increase the resistance, we get speed below base speed at the constant torque. For variable flux method, we decrease the flux, we get speed above base speed at constant power. Okay, this is the main thing that we need to remember. This was for DC shunt motor and separately excited. Same happens for DC series also, only difference is there in their formula. Okay, because we have different formula for torque formula. We know that because field flux, field winding is connected in series with the armature, that's why there is a little bit difference. Everything remains same. Okay, voltage control and armature, voltage control and resistance control remains same, only difference come in flux control. Okay, for flux control, in case of a shunt and separately, we directly decrease the IF. Okay, but in case of DC series motor, we cannot decrease the IF directly. If we decrease the IF, because in case of DC series motor, IF equals to IA. If we decrease the IF, means we are decreasing the load. Okay, it means we are decreasing the load. See, here we have discussed, if we are decreasing the IA, if we are decreasing to reduce the field flux of a DC series motor, we need to reduce IA. But if IA is reduced, in torque induced will reduce and it will become unstable, so we cannot do this. Okay, so alternate method we have is an alternate method to reduce flux in DC series is we use diverter, or we do tapping, or we do series parallel of the this field winding. Okay, series parallel. See, this way we use diverter. Okay, if we divert the current by this way, and then if we divert the current this way, then overall field will decrease. Okay, if field will decrease, then E will decrease. Then if E decreases, then IA increases. If IA increases, then induced torque increases and speed will increase at above base speed with power constant. Okay, if we decrease the field by using tapping, this way also we can do, and by series parallel. Okay, if we keep it in series, and then what will happen? See, accordingly we can do. Okay, we can control this way. Okay, and another method of speed control is by Ward-Leonard method. Okay, with this method of speed control, we can do both. We can decrease the speed. We can decrease the speed below base speed, and also we can increase the speed above base speed with this Ward-Leonard method of DC motor speed control. Okay, here basically speed below the base speed is obtained by decreasing the armature, by decreasing the armature voltage, by decreasing the terminal voltage. Okay, and speed above base speed is obtained by decreasing the field flux. Okay, by decreasing the field flux. See, if we are in this setup, what we do is we have to control the speed of this DC motor. Okay, for that what we need to do, we have to do a setup of we need to control the speed of this motor, we need one DC generator of same rating, okay, DC generator, and a three phase and a okay, we need DC generator and a motor, okay. So to rotate this generator, we use three phase induction motor, okay. And the output of generator is connected to the input of motor, and field flux is connected, field winding of both motor and generator is connected to a single supply with variable resistances, okay, that is RH1 and RH2, okay, with variable resistances, okay. Now when we see in this setup, we can easily understand the working. When we decrease the resistance 1, then what will happen? Field of this generator will decrease, okay. If field of this generator will decrease, then its output induced EMF will reduce, okay. If induced EMF will reduce, then it means that terminal voltage of a motor is reducing. If terminal voltage of a motor will reduce, that is armature voltage control, okay. If terminal voltage of a motor will reduce, then obviously the speed will be below base speed, okay. See, we got speed below base speed. And when we increase the resistance of this field of motor, what will happen? If we increase the resistance, then field winding, then the field flux of motor will reduce. If field flux of motor will reduce, then speed of motor will increase above the base speed. So in this way, working of a Ward-Leonard method is done. Now, starting method of a DC motor. This topic is currently removed from the GATE syllabus, but still it's better to know little bit, okay. So why we use a starting method of a motor? We use basically a starting method to reduce the starting current, because starting current is very harmful for the motor, okay. That's why we use the starting method, okay. When we talk starting, there are for DC shunt motor, we have a 3-phase starter and four point starter, okay. We have 3-point starter and 4-point starter. And for DC series motor, we have a 2-point starter, okay. We have 2-point starter. So for 3-point starter, start motor by adding many resistances at starting and gradually removing all resistances, okay. Open OLC is for protection, okay. An overload coil is used for protection. Speed control by varying field is not possible here, okay. In 3-point starter, speed control by varying flux is not possible, so we go for 4-point starter, okay. So we go for 4-point starter, okay. Now, braking method of a DC motor, okay. We use braking method to immediately stop the motor, okay. To stop the motor, we have 3 methods: dynamic braking, plugging, and regenerative braking. In dynamic braking, VS is replaced by external resistance, okay. Source voltage is replaced by external resistance, so negative torque is developed. Due to this negative torque, motor stops quickly, okay. And remember that field flux is kept constant, okay. And in case of plugging, we will reverse the polarity, keeping the field flux constant, and also we use external resistance, okay, to avoid the armature current, okay. We use external resistance. And for regenerative braking, what we have, this is the most effective method. This is a very efficient method, because in this what we do is we store the kinetic energy in the battery, okay. Here VS is reduced stepwise, so it develops negative torque, and kinetic energy is stored in the battery. Very efficient method, okay. This one is very efficient method. And Now for parallel operation of DC generator, for separately excited and shunt DC generator, polarity must be same. Okay, polarity must be same. For same RA, if armature resistance of both the machine is same, then if induced EMF is higher, higher induced EMF generator will share more load. For same induced EMF, higher resistance will share less load. Okay, remember this. And for DC series generator, if any of the generator supply more current, then gradually that very generator will be overloaded and other generator will become motor. Okay, so for DC series for DC series generator parallel operation, we need to use equalizer. Okay, in this technique we separate field winding and armature winding. See, in this way we have to do. This is armature part, okay, and this one is field part. Okay, in this way we have to do parallel operation of a DC series generator. Okay, so next we have testing of DC machine. Testing of a DC machine is done to know losses and efficiency. Okay, this is only the reason of doing testing. So we have direct test and indirect test. Okay, in the direct test, what we do is we need rated load. We need to give rated load and input. Okay, and for a small rating, this direct test is only done for a small motors. Okay, we have to give rated input and rated load. So we do in that way we do the direct testing. This is very easy and very accurate method is, and this is only used for a small rating. For higher rating of machine, we cannot do this type of direct testing, because there we will need because that will become costly, because there we have to put rated input and put rated load. Lots of energy will get wasted. Okay, that's why we don't use for a higher rating machine. So we use indirect method for testing. Okay, they are like Swinburne test, Swinburne method, Hopkinson test, field test, retardation test. Okay, these all tests we need to keep in mind. Swinburne, Hopkinson, field, retardation. In Swinburne method, what we do is, in Swinburne method, need to run at no load. So not for DC series motor. Okay, we need to run at no load. In Swinburne method, we need to run the machine at no load. Okay, so we know that we cannot run the DC series motor at no load, so we cannot apply Swinburne method on DC series motor. We can apply it only on shunt and separately excited. This is used to find rotational loss. Okay, and for Hopkinson test, that is also called regenerative test. In this we need two similar DC machine or separately excited. Power input to this set is equal to losses. Okay, and for field test we use for DC series machine. Okay, and retardation test is done in two phase. Okay, turn off the motor without field flux. Okay, turn off supply without field flux. Rate of change of kinetic energy is equal to mechanical loss. Okay, and turn off the motion, turn off with field flux. Rate of change of kinetic energy is equal to mechanical loss plus core loss. And in Hopkinson test, that is regenerative test, for DC shunt and separately excited, two similar DC shunt machine are mechanically and electrically joined. Okay, and one machine is motor and other is a generator. Total input to above set, okay, is equal to losses of both machine, armature copper loss plus rotational loss for both. Okay, and efficiency is same, that is root under I2 square, I2 upon I1. Okay, and rotational loss of machine 1 is equal to omega naught upon 2 okay, and that is v1 I1 minus I. This is the formula, okay. And E in EA1 is less than EA2, then EMF of motor is less than the EMF of generator, okay. Phi 1 is less than phi 2, it means phi 1 is less than phi 2. And IF1 field current of 1 is less than field current of 2. Field current of motor is less than the field current of generator. IA1 is greater than IA2. Armature current of motor is more than the generator, okay. Therefore armature reaction of motor is more than the armature reaction of generator. Therefore demagnetization effect of motor is more than the demagnetization effect of generator. In field test for DC series, field test is like this. See, two similar method. One machine DC series and other is DC separately excited, okay. We have power input, power output. Power input minus power output equals to IA into RA plus this, and okay. So we get rotational loss equal to omega naught upon 2, okay. See, in this way we have to do connections, okay. So when we talk about a runaway condition, now let's study the runaway condition. Assume field is weak and IA is high, okay. Assume field is weak and IA is high, therefore armature reaction will be more. Armature reaction more means demagnetization effect is more, means field flux will become weaker, okay. Overall flux will become weaker, therefore speed will increase. If speed increases, then load torque will increase, okay, because load is linear. Load torque increases means electromagnetic torque will increase. If electromagnetic torque increases, then IA will increase, and again armature reaction will increase, and same process will repeat. Finally motor retains very high speed and motor may get damage, okay. And for stabilizing winding, now let's study about stabilizing winding. Due to armature reaction effect, demagnetization effect increases, okay. Demagnetization effect increase. To balance it, one of you turn on field winding in series, that is cumulative compound, okay. Cumulatively we have to wind, and therefore if IA increase, then armature reaction increase, and then demagnetization effect increase. If we increase the if we connect a series field, okay, then overall phi will increase, okay. If phi increase, then it will balance the demagnetizing effect, okay. Now, if field flux increase, then it will balance the demagnetization. That is stabilizing winding, okay.